So in this video we're looking at networks. This is 2.1 of the CIE 9618 A-Level Computer Science course, but a lot of this applies to other exam boards as well. This is quite a long section and this video will be quite long, so chunk it up, break it down into different parts and watch just the bits as you wish. We'll start with a definition of a network. What is a network? It's two or more computers that are connected together to share information and resources, share data, resources. So you can't do that with one computer. We need at least two, and of course nowadays networks contain millions of computers. So why would we want to connect computers together? The benefits are that we can share files and we can collaborate, i.e. work together on a document, a file, and we can do this remotely. We can do shared hardware, so we don't need to buy a printer for everybody. We can have, say, one large printer and share it amongst lots of users. Same for storage. We can have servers for storing data and share those servers amongst lots of people. It also allows us to do centralized management of things like security and backups. So every individual user computer doesn't need to do all those things. It also allows for communication. We can do things like email, instant messaging, video conferencing once we have a network. So there's a lot of really good reasons for having networks. There are different types of network. Let's start with LANs. LAN is a local area network. This is something that covers a small geographical area. It could be a home, a school, an office, a factory, but one localized area. And it's usually, all the equipment is usually owned and maintained by the organization itself. Connections can be very high speed. They can be both wired and wireless connections within the LAN. Compare that with a WAN, a wide area network. This covers a larger geographical area. It could be the entire world, like the internet, or it could be a city. It's made up of multiple connected LANs. So we have LANs, but then we connect them together and we effectively create a WAN because they cover more than just one local geographical area. And then it may not all be owned by one organization. It may be owned by lots of different organizations. Some may be public, some is private. It could be using things like leased communication lines that, effectively is borrowing from somebody else. Another way of looking at different networks is to look at the models, how they work, how they behave. And the first one we look at is client-server. In a client-server architecture, we have two distinct roles. One device acts as a client requesting data or services from a server, and the other one acts as the server to provide or respond to the requests. Now the server can decide whether to respond or not to a request. So the server is in charge. The client is just asking and the server decides. The advantage of doing this is that we can have centralized control. It's easier to do things like updates. We can push them out from the server because the server is in charge. And we can maintain security better because we have one point that we really need to secure. However, the disadvantages are, if the server fails, then none of the clients can get access to what they want. It also typically would involve a higher cost because the server has to be a specialized piece of hardware to manage all the requests from clients. So it needs to be designed and built to manage that demand. Contrast that with the peer-to-peer model of network behavior. And in this one, every peer can act as both the client and server at the same time. So they don't have a permanent role, a fixed role. They can do anything. We don't need a dedicated server for this, so that reduces cost. You just have the devices you would have anyway. And it's easy to set up, so you don't need a special piece of hardware. You don't need to set that up somewhere. You don't need to connect it up to everything. You just have the normal computers, and those computers can talk to each other backwards and forwards at any time, requesting, sending. Um, there's no restriction. They're all considered to be equal in terms of status. However, this is less secure. There's no central point of control. Devices can do what they want. And so, for example, sending updates for software to all these computers is difficult because you're not able to do that from a single point. Another way of looking at networks is to look at thin versus thick clients. A thin client has little processing locally or little power and storage locally, so it relies on a separate server to do most of the processing and storing of data. This is a cheap way of implementing computers for users. So the terminals, the clients, can be very basic computers without much power and storage. That makes them cheap. However, you do then need a powerful enough server to manage all the requests that you get from all those clients. In a thick client, you have storage and processing power locally, as well as having access to a server. General purpose computers can be used as the clients in that case, and they can do a lot themselves without having to rely on the server. So if the server doesn't work, the clients can still carry on working and doing things, but it also can take advantage of server if it wants to. And yet another way of looking at networks is to look at the topologies. In this case, we're talking about physical topology, which means how the devices are actually placed physically and how the connections are made between the devices. A logical topology would look at actually how the data moves through the network, regardless of the physical topology. So they can actually be different. The physical can be set up one way, but it can actually behave logically in another way. Now, the topology you choose can affect network performance, how scalable the network is, how good security is, and how reliable it is. So it's an important consideration when setting up a network. One of the network topologies, a physical topology, is called the bus topology. In this topology, all devices share a single cable. So you can see in the middle of the diagram there, we've got the single bus, the cable, that all the devices are then connected to. This is easy to set up, relatively speaking, but there's a lot of reliance on this single cable. So if that fails, then none of the devices can talk to each other. It's also prone to collisions because they all send the messages along the same cable, and then sometimes those messages clash with each other. It's called a collision, and they have to start resending data. The security is quite weak on this topology because when this device, for example, is sending a message, then it has to go past lots of other devices who all get to see that message that was sent, even though it's not for them. In the topology, we have the devices that are connected up, and at the end we have something called a terminator, and the terminator is to stop the messages once they get to the end. Okay. A star topology is an alternative to bus topology. In this one, we have a central, typically switch in the middle, and all the devices have their own dedicated connection to that switch. So if device 1 wants to talk to device 4, then device 1 sends a message to the switch, and the switch forwards it to device 4. It only needs to go to device 4, so all the other devices don't actually get to see the message. Only device 1 sending it to device 4 see the message. This is more reliable because there isn't a reliance on a single bus. So a cable here, for example, could break and the other devices will still be able to work fine It's just device 6 with its cable that's broken that would not be able to communicate. It requires more cabling, so it's harder to install. If you imagine trying to install this in an actual building, these connections might have to go through walls, long distances around the building. The more wires you've got, the harder that's going to be. It's relatively easy to add additional devices, i.e. the scalability. You can just add more and more, plug them into the switch. When the switch runs out of ports for you to plug into, you can add another switch and plug them in together, and then that expands that way. It's better for security because the messages only go through to the intended recipients and not everybody. They're not broadcast to everybody like a bus. And then we have something called mesh. In a mesh, you can have a full mesh where every single device is connected to every single other device. That's expensive and difficult to set up. Again, the wiring becomes a bit of a nightmare. There's a thing called a partial mesh, which has multiple connections, but not necessarily every device connected to every other device. And the main advantage of this particular kind of topology is it makes it extremely robust and reliable. Multiple lines could fail and devices can all talk to each other still. Obviously, eventually you're going to get to the point where some can't communicate, but it is the most robust of the topologies. It's expensive and complex to install though. Now, in all of these, packets are actually sent between the devices in the networks. So if we're using something called packet switching, and we'll be sending packets of data around. So depending on the topology that we're using, the way the packets actually transmit is different. In a bus topology, then there's a single cable and all the packets have to go along that single cable. And they get to the terminators and it stops it from reflecting back, so it terminates, it ends the packet at the end. Signals go in both directions along the cable, and every device gets to see it, as we've seen before. So what happens is each one of these devices has a network interface card that will check the packets that come past it and check to see whether or not it's intended for them or not. So it does that by looking within the packet itself and look at the frame header and seeing whether or not the address matches it. And because they all share the same cable, we do have a problem with transmitting packets. If two of them try to communicate and send packet at exactly the same time, then a collision can occur between those packets. There are ways around this. We can use techniques such as CSMA and CD, and this is where they will try and avoid the collisions. In the star topology, because we have dedicated connections between them, then packets can be sent directly from one device to the other device via the switch. So the packet itself can only go to the one that it needs to go to. The switch itself will work out where to forward the packet to using a table. Within the packets you have an address, a MAC address of the device that you want to go to. Those MAC addresses are unique for every single hardware device, or should be. So it can use a table. Once it's worked out what the MAC address is for all these devices, it can send it to only the one that it needs to. And in mesh, the packets may go directly from one device to another device, or it may need to be relayed along the way by another device, like an intermediate device. Obviously, security-wise, it's good when it goes direct to another device, but not so good it has to go and be relayed by another device. Now we move on to cloud computing. So this is a term given to computing that's done remotely So remote servers will carry out processing or store data for you. Um, it can be public or private cloud computing. Public cloud, then you're using resources that are provided by somebody else, and anybody can pay and use those services, not just your company or your organization. A private cloud would be your own. So an organization may have their own cloud that they set up, their own servers somewhere, but they're still accessed remotely. So it may be in another building, may even be in another country, but everybody can access it via the internet. Um, Benefits of using cloud computing. It allows scalability. You can have as much processing power or storage as you need. You can start off with very little and build up and then go back down again if you need to. So as companies grow and contract, they can adjust accordingly. You're not locked into having a certain amount of power or storage. You can access it from anywhere in the world. And usually these things come with very good security and backups that are automatically done for you, so you don't have to worry about that yourself. Drawbacks though, it does rely on the internet connections. There are potential security issues, so you're not directly in control of what happens with your data. You have to rely on a third party and trust them to be handling your data appropriately and safely. It can potentially have higher cost. Um, you may end up paying more overall, and effectively you're paying for flexibility and the other features that you get with it, like the backups and security and so on. Whereas if you were to do it yourself, the storage might be cheaper, but then you'd actually have to do work yourself. Also, you tend to get slower access speeds because you're going through a network. There's delays in that. There's lag and latency to get your actual data. And if you have a bad internet connection, then it can be really slow. We also have different connection methods. So we have wired and wireless networks. There's various types. Wired connections can be things like copper cable. They're used in Ethernet. It's relatively cheap, not as fast as fiber, and because it uses electrical cable, it is prone to electronic interference. Fiber optic cable is very high speed. It's a bit more expensive. It is resistant to interference, and more fiber optic cable is being laid all the time and replacing some of the copper cables that were being used before. Wireless methods, typically using things like radio waves. For example, Wi-Fi uses radio waves. It's convenient, has a shorter range, and there are security risks if it's unprotected. So you have to encrypt your data and take other security measures to make sure that your wireless transmission is safe. You also use microwaves, for example, point-to-point links sometimes use this. It does require a line of sight though, which sometimes you see microwave dishes on top of buildings pointing in different directions to obviously make a connection to another point somewhere else. Can use satellites, but they are relatively speaking a long way away, and you do therefore get quite a bit of latency in them. So it's actually preferable to use fiber optic cables on land or under the sea rather than going via satellites. Let's have a look at some of the network hardware you'll need to set up networks like this. First one is a switch. Switch connects devices within a LAN, and it directs data only to intended recipients. So we've seen once it's learnt where all the devices are. A router, quite different. It connects two separate networks. For example, a LAN connecting to the internet, that would be done by a router. So a router is sort of in the middle of two networks between I should say, two networks. For example, the LAN and a WAN. Network interface card is something that's built into every single device that wants to connect to the network. It may be called a network interface card, network interface controller. It's the same thing. If it's a wireless one, again, there are different names for it, like a wireless network adapter or a wireless NIC. So these are the same thing. They do the same job. Allow the device to connect to a network. There's a wireless access point. This is something that you'll see around buildings very often to give signal in places where the router itself can't reach. It allows for wireless connections to the network. So your device, say for example in a classroom, would connect to the wireless access point locally, maybe in the corridor or in the classroom itself, and then that would be connected up to the network and the router via wires. A bridge is used to connect separate network segments. We'll look at network segmentation later, but basically you can separate your network out into different parts. Repeater is used to boost signals, extending the range. You may find the problem that the router can't transmit, say, into another room in your house or into the garden. If you've got a big house, it can be more problematic. So sometimes you need a booster or extender in order to help with that. And then you've got the cables themselves. Of course, this is all hardware, and hardware is the things that are physical devices or components, things that you can touch. So included in that is cables. And again, we have things like fiber optic cable and twisted pair copper cable. So we take a look at the router a little bit more. The job of the router is to basically receive packets of data and then to work out where to forward them to. So it's packet routing, forwarding. And it's going to look at the packets to work out how to do that and where to send them. It also does something called network address translation, or NAT. This allows you to have multiple devices in your LAN, your local area, share a single public IP address, and then it will translate IP addresses when they come in, so that it will go to the correct device on your LAN, and also on the way out it will replace the address, the local address that you have within your network, and into the one that's going out and to be seen publicly. Many routers also have built into them various other things like switches and wireless access points, so that makes them multifunction devices. It carries out security for you, something called packet filtering, firewalls. So it'll look at the packets of data coming in, check them, see if it thinks they're legitimate, or if they were unsolicited packets coming in, i.e. they weren't requested, then they can reject them. They provide support for Ethernet and for CSMA CD, so it will carry out some of those processes. It also allows for bit streaming, this, i.e. the transmission of bits between devices. So we've talked a little bit about this issue you get sometimes. It can happen on Ethernet, where you get collisions where devices are trying to broadcast packets or send packets at the same time. So CSMA CD does this. First thing is, before trying to send data, a device will listen, so detect to see what's on the line on the network connections, and if it finds that there is traffic on there already, it will wait. So it won't try and send if the line is busy. If the line's free, it will transmit its data. But if another device has also transmitted its data at exactly the same time, i.e. they both listened, they both decided it was free, the line's free, and they both transmit at the same time, then we could get a collision. And we need to detect collisions. If we detect that that's happened, so both devices will be try to work out whether their packet were collided or not. And if they do, they each wait a random amount of time and then they try again, which means that the next time, hopefully, they won't clash again, they won't have another collision, and it'll work. However, another collision could occur, in which case we wait random time again, but that random wait time starts to increase. So each time, if it gets repeated collisions, one after the other, then that wait time starts to get increasing, and until hopefully you get to the point where there's less traffic on the network because everybody's waiting longer, and then you'll be able to get your message through. We mentioned bit streaming a moment ago, so let's look at that a bit more. It means the continuous transfer or the continuous sending of data bits over a network. We have real-time streaming, where the data is being produced live. It's not pre-recorded. So a video call would be real-time streaming. And for this to work well, we need really a steady connection. If it's fast sometimes and then very slow or stops at other times, then this can be very problematic for live data because we've got nothing to fall back on. We can only send it as soon as it's generated. Another example would be on-demand streaming. So this is where there is a pre-recorded file and we stream it when it's requested. That's not so dependent upon the connection, although we still need a fairly good connection to do this. It does mean to say that we can buffer some of the data, and when the connection is slower, we can use some of that pre-recorded data that's held in a buffer to keep the user busy, to keep them entertained until the connection improves again. So bitrate is how quickly you can send bits, and so for example, you might have a broadband internet connection with a maximum bit rate of say 20 megabits per second. That's a bit rate, but that varies. Okay, so it's not always going to hit your maximum. Sometimes it will a lot slower. So if your bit rate is too low, then you will need to you will get poorer quality experience. You'll have interruptions, you'll have buffering, you'll need to wait until the bit rate is fast enough and you can catch up. So now we're looking at the World Wide Web versus the internet. A lot of people in the world confuse the two terms or use them synonymously. They're not. So the internet is the network of computers. It's called the infrastructure. It's a bit like the road network in a country or in the world indeed. It's all of the actual physical parts of the network. The World Wide Web is a collection of web pages that are hosted on servers and they're accessed via the internet. So it's a bit like saying they're people that you can visit. You have to use the infrastructure, you have to use the roads, and then you can go and visit somebody. And that's like the analogy for the internet versus the World Wide Web. The World Wide Web is just one of numerous things that are actually stored and accessed via the internet. We can also use it for things like email and games and files, so not just the World Wide Web. So those two terms are quite different. Some more about internet hardware. We still have some of this left, is the PSTN, the traditional telephone wire network. And originally that was only designed for voice calls, and it wasn't really meant for computers to talk, but we managed to make that work by using something called modems originally. So the traditional telephone wire network was an analog system for analog calls and using voltages to represent the people speaking in a analog way. But for computers, we need a digital way of talking. So we introduced a hardware device called a modem, which can modulate and demodulate. That means convert from analog to digital and digital to analog. Later on, these were adapted from using sort of analog tones to using digital transmission instead. Nowadays, we're replacing a lot of that old copper cable telephone network with fiber optic. So in this country, in the UK, for example, more and more houses are having the last part, it's called the last mile, where they're replacing copper now with fiber. So you're able to get very much improved speeds, broadband speeds, by using fiber optic cable. Dedicated lines are what we call a permanent point-to-point connection that's specifically reserved for a single customer, or at particular times can be reserved for one particular customer. Then you have the cell phone network as well. So mobile phones obviously now support internet connections. Originally they didn't, but we've got things like 4G, 5G now to allow for data connectivity. They use the core network once you've gone beyond what's called the access network. So your mobile phone has a radio transmitter and receiver in it. That will go to a cellular tower, and from the tower on, then it's using a network itself, and mobile data uses that network to send data around. IP addressing is how we identify devices on a network. There's IPv4 and IPv6. 4 is older and stores addresses as a group of 4 numbers. Each number is 8 bits. So for example, 192.168.1.1, that's 4 8-bit numbers. The maximum number you could have there obviously is 255. So you've got 0 to 255 in each one of those 4. Now that doesn't really give enough combinations for the amount of devices we connect to networks these days. So IPv6 allows for much more addresses. It's an incredibly huge number of addresses available. The format is different. We write things down in hex, and it's 4 hex digits, and you can replace, this is a shortened version, you can replace bunches of zeros with colons, and you can also omit leading zeros in numbers just to make it shorter to write, because they are very long. I think those are 128 bits long, okay, whereas these are only 32 bits long. So massive amount of values you can have in these, and hopefully we'll never run out of them like we did with IPv4. These are used alongside each other still, so it's backwards compatible. You can still use and see IPv4 addresses on networks, but you also see IPv6 ones. Subnetting is a way of dividing up a network into smaller subnetworks. This can help with various things, including the management and security of different parts of the network. Public IP address is one that is visible on the internet. Anybody can see your public IP address. It has to be a unique address at that time on the network, so you know exactly where that device is, and anybody can find it and see it. Private IP addresses are only used within a local network, so devices outside of your network, so your local area network, can't see those IP addresses, and you can't directly talk to those devices from outside. You'd have to go through the router and do the network address translation. A static IP address one is one that's fixed. It doesn't change each time you log on, each time you connect to the network. It stays the same. So for example, servers would have a fixed static IP address so that you can find them again. You don't have to search for them all the time. They're always going to be in the same place. A dynamic IP address is one that changes periodically. So for example, when you connect and then reconnect, you might have a different IP address. It can change more often than that, and it's assigned by the DHCP. Obviously, one of the reasons we have dynamic addresses is because when we were using IPv4, we started to run out, so we only wanted to have the ones being used for devices that were actually connected, rather than ones that might connect, so that we could make more efficient use of the available IP addresses. So a little bit more of a look at subnetting, where we take a large network and split it up into smaller parts. Those parts are called subnets. And what we do with IP addresses is we assign different parts to the IP address. Some of the IP address refers to a network, and some of it refers to a host. And we can play around with that demarcation between the two to create our subnets. So a subnet mask will tell you where that split happens, where that differentiation between the network and the host occurs in your address. So you might have something like that, 192.168.1.0 with a mask of 255.255.255.0. That's sometimes written as /24. And that means that the first 24 bits out of the 32 identify the network, and that means the last 8 bits identify the hosts. So that means you can have 256 different hosts addresses on that network address. Only 254 of those are usable because the other two have special uses. So those two addresses that are reserved and have the special uses indicate are in the first address and the last address. So the very first one, the 0 one, and the very last one, 255. Those two have particular meanings. So the first one is used to identify the subnet itself. So the 0 value is just used when you want to refer to the entire subnet and not an individual device within that subnet. And the last one is used when you want to actually communicate with all of the devices in the subnet. So you might see something like this is a subnet table. We've divided our network into 4 subnets. This is the network address, i.e. the beginning of that block of addresses. This is the range of values we can have. So this is the 0, 1. That's just used to identify the network, the subnet itself. So we can't use 0. We start at 1. And then we can go up to 62. Because 63 would be used to broadcast to all the devices in this subnet. And then the next one is 64. So we can use it from 65 to 126 and so on. If you want to split your network into smaller subnets, you need to take more bits away from the host portion and give them to the network portion instead. So you move that line where you're splitting the IP address. For each bit you borrow, you can double the number of subnets you can create, but you have to halve the number of hosts you can have. So we could take something like a split 192.168.1.0.24. If you want to split that into 4 subnets, you need extra bits. How many extra bits do you need? Well, to represent 4 different values, you need 2 to the power 2. So you need 2 bits. And then we extend the mask. So it's no longer 24, it's 26. So we're using 26 bits instead of 24 bits. And then each of the resulting subnets has what's left. And instead of 2 to the 8, we've got 2 to the 6. 64 addresses, and of those 62 can be used for devices, with the other 2 being used for the special purposes we looked at before. So why do we subnet? One of the reasons is it reduces the broadcast traffic. So If we don't split into subnets, then when we send out packets, it could be sent to all of the devices within that network. If we subnet, then we can make sure that the packets of data are only going to devices within one subnet rather than the whole network, which means that a lot of bandwidth can be saved and not wasted. It can improve security, so we can separate subnets and isolate them from each other. For example, we could have a guest Wi-Fi subnet that's not connected to our sensitive data and resources, and guests only sit within that subnet, and they have different access and rights. It also allows us to have some kind of logical management structure. We could, for example, have subnets and group devices by a department within an organization, by a physical floor of the building, or a function, the sort of job role that people do. And that way we can make it easier to monitor, set policies, and work out where things are going wrong. Let's look at domain name service. So domain name service, its job there is to convert what we like as humans, the written addresses like www.example.com, into the numbers or IP addresses that the computers want to use. So when we're using domain name service, what happens when we enter a web address into a browser? So you type in your web address in the normal way, in the way that we like as humans. We type in our address. That's easier to remember than a number. Uh, the client, i.e. the software on your computer that's making the request for this web page to a server, is going to send a message to a nearby domain name server. Uh, the domain name server, in this case typically your internet service provider's DNS, that's going to check to see if it knows what the IP address is for your website or your URL. If it can't find it on its own server, then it'll go to another domain name server until it finds one that does have that matching IP address to the URL. And then it's passed back through those domain name servers, and each one will cache it and save it in case it gets asked for it again. And then it all comes all the way back to your client. So the browser in your client will have access now to the correct IP address for that website you were trying to look at. Okay, that was networking. And next time we're going to be looking at computer hardware.